video, all right? All right. So now that we know this, let's make an example, right? All of this is seen a little bit better when we use it in an example. All right, so here we go. Let's use an example. How can we find what is the value of I to the 18th power? I to the 18th. All right, one way of finding this number is to continue this this progression, right? You can continue this progression. Find the I to the 9, I to the 10th, I to the 11th, I to the 12th, all of that. You can do that. And eventually, if you continue with the progress, you will find I to the 18th power, right? Now remember, these values are always going to repeat. So we have I, negative 1, I, negative 1, negative I, 1. I, negative 1, negative I, 1. If you were to continue this, you will have again I, negative 1, negative I, 1. So there is a pattern, right? And you can continue that pattern all the way up to I to the 18. But there is an easier way. There is an easier way. Look at this. We can separate these values. We can separate them, right? We know that I to the 18 is the same as I to the 16th times I to the second power. We know that because of the properties of the exponents, properties of powers, right? Whenever we have a multiplication of powers, and they have the same base, we can add the exponents. Remember that? So that is what we did in here. We split the 18 by 16 and 2. And now we can do the same with 16. 16 is the same as 4 to the 4. Again, another property of powers. This is power of a power, right? Whenever we have a power of a power, we leave the same base and multiply the exponents. So we have 4 times 4, which is 16. But now we know these values. We know the value of I to the 4, 1, look at that. And we know the value of I to the second power, negative 1. So I to the 4th power is 1. 1 to the 4th power is 1 as well. 1 times I to the second power is I to the second power. And that will be negative 1. Did you see what I did? All right. Go ahead and write it in the chat, please, if you guys understood this. If you didn't, you can just let me know and I can
explain. I didn't understand so well.
You didn't. All right. Okay. I'll do it in the board. There we go. All right. Let's leave this in here for a minute. All right. So the question is, how much is I to the 18th power, right? That is the question. How much is I to the 18th power? How much is that? All right. So we can continue with the progress. As I said, we can continue with the progress, all that I to the 1, to the 2, to the 3, 4, 5, 6, 7, 8. And we can continue all the way until A to the 18th power, I to the 18th. But there has to be an easier way, like this. We know that I to the 18th power can be expressed as I to the 16 times I to the second power, right? We know that. We know that because whenever we multiply these, since they are powers, we are going to leave the same base and add the exponents, right? So that is good mathematics. You can do that, right? But now, look at this. We can even express this even further beyond. Look at this. I to the 16 is the same as I to the 4th power elevated to the 4th power. And this is times I to the second power, all right? Look at what I'm doing. I to the 4th power to the 4th power, well, what we have here is a power of a power. So we have a multiplication of exponents. 4 times 4 is 16. So this I to the 16 I can express it as I to the fourth to the fourth. Eh? Now, if you guys understood the explanation all the way up to here, please write it in the chat. Write yes or write no. That way I know what is it that I have to explain. Did you guys get it all the way over here? Lonita, please write down as well.
Profe, yo tengo una pregunta.
Yes.
¿Me puedes explicar qué fue lo que pasó con I a la 2, a la 4, perdón?
Sure. I'm on my way, buddy. Of course. All right, beautiful. All right. Now, let's continue. Now, let's get to the fun part. This is some basics of properties of exponents, right? This is basic stuff. Now, let's jump into the important part. Look at this. We know how much is I to the fourth power. We know how much is that. That, according to our little table, that is 1, right? Look at that. That's what it says over there. That's what over there, right? I to the fourth. There, I to the fourth. Eh? So we know from here, we know. This is I to the fourth, which is 1 to the fourth power. Look at that. I to the fourth is 1, but don't forget about the second fourth. It is right there. Times I to the second. But we know how much is I to the second. We know how much is I to the second power. Look at that. It is right there. Look, right there. I to the second power, right there. It is -1. So this is 1 to the fourth times -1. -1. Huh? Now, please, in the chat, guys, go ahead and write if you understood this line. What I did from here to there. Okay, all right, beautiful. All right. So I'm gonna continue then. All right. Remember, if you didn't, if there's something, teacher, I don't know why. What is this one? What is this for? If you didn't, just let me know. I will explain it again. All right.
No, profe, es que no entiendo, es como, no en ese ejercicio, sino en como tal en el I a la 2, ¿cómo se hizo para llegar a 1? ¿Sí me entiendes?
En el I a la 4, ¿no?
Eso, I a la 4.
Okay. All right, sure. Let me continue with this, and then I'll go back and explain the I to the fourth, all right?
Okay.
All right, sure. Now, let's find the solution of this. This is one of those exercises that I am sure, if you guys study with Miss Sasha, I am sure whenever you were presented with exponents, you had something like this. I am sure this is a 6th grade question because all we have to do is now multiply by ones and negative ones. 1 to the fourth, this 1 to the fourth is the same as 1, right? So we have 1 times -1. And how much is 1 times -1? Well, that is -1. So we know I to the 18th power is -1. Here is our solution. And that is the process we do. Now, with this type of process, we can find questions like this. How much is I to the 1,000? How much is that? Now, of course, if you did the progression all the way to I to the 18th, you found this solution, -1. But let me ask you something. Are you going to do the progression 1,000 times? You can. You can. But I assure you, it's going to take you a lot of time. So there has to be a trick. There has to be a trick. I'll show you the trick later. All right. Let's make a little note here because Richie wanted me to explain little review. Richie wanted me to explain how did I jump to I to the fourth to 1. To 1. Simple here. This is 1 simply because look, I to the 4th power is the same as I to the 2nd power times I to the 2nd power. Yes or no? And now we can see it. Now we can see it because by definition, whenever we have the 2nd power, this is -1. And we have 2, so this is -1 as well. -1 times -1 is +1. Checks out, right? But we can do it in another way. I am sure some of you are seeing it. We can do it in a different way. We can say, how much is I to the 4th? Remember, this is the question, right? Okay, I to the 4th is the same as I to the 2nd power to the 2nd power. Power of a power. If I multiply the exponents, that's a 4 as well. So I can do that as well, right? I can express the I to the 4th in 2 ways. All right. If I do so, I to the 2nd power by definition is -1. So what we have here is -1 to the 2nd power. And how much is -1 to the 2nd power? All right, since it's negative, the result is going to be positive, and 1 to the 2nd power is just 1. So again, it checks out. No matter what process, what steps you take, it checks out. Huh? Beautiful, beautiful stuff here. Beautiful stuff here. All right, that's the reason, Richie. That is the reason.
Mr. So why in the example of the how in the presentation the class
Okay.
note says like -I times I?
Because what they did is they splitted the I to the 4th, not like I did, to the 2 to the 2 or to the 2 to the 2nd power. No. But they split it as 3 and 1. It checks out as well. Look, let me erase here and I'll do it in this part. What they did is this. I to the 4th power can be expressed as I to the 3rd power times I to the 1st power. Right? It works because they have the same base. So we leave the base and we add the exponents because we have a multiplication. So 3 plus 1, 4. It works, right? And all we have to do is go back in our table and find the values of I to the 3 and I to the 1. All right. I to the 1, that thing is absolutely easy. That is just I. I to the 1 is I, right? It is every number elevated to the 1 is the same number. So that is I. But how much is I to the 3? According to our table, is -1. I'm sorry, -I. Right? So what we have here is -I times I. That is what the presentation has. -I times I. Now, if you multiply this, if you do the multiplication, you have -I to the 2nd power. That is what you have. The negative outside. Look, I am not doing a parenthesis. I am leaving the parenthesis outside. Right? Okay? Now, we have negative because of the negative on top, but how much is I to the 2nd power? I to the 2nd power. I to the 2nd power is -1. So we have -1, which is in total +1. Again, checks out. No matter what way you choose to split it, it's going to give you 1. Eh? Eh?
So, teacher, it doesn't matter what combination of number we use, it always will give you the same answer.
Yes, Danny.
Just
You
at
are
least the combination of numbers makes 4 in this case.
beautiful. Yes, sir. You are right. You are correct. Now, as you said, it doesn't matter what combination you use. But the question is, knowing that there are a ton of possibilities, which one do you choose? Choose the easiest. In my mind, the easiest is this one. I to the 2 times I to the 2. Now, the reason why I leave this one in the slides is because this one is the one that the video is presenting to you. And I want to have that coherence. You know what I mean? But I wanted to show you this possible presentation as well. I to the 2 times I to the 2 is I to the 4. So it works. It works, right? It works. All right, guys. Let's continue with this. Let's continue with the example. All right, let's see. Beautiful. Now, let's go with complex numbers. This is the real part, the real interesting part. Complex numbers, right? Complex numbers. Now, complex numbers are numbers in the form a plus bi, right? And a and b are regular numbers. I'm going to do some examples of this. Look. A is called the real part, b is called the imaginary, and I is called the imaginary unit, the little letter that we all just learned, the square root of -1. All right? Now, I'm going to do some examples of this. Let me change into the other presentation. There we go. I'm going to do some examples of this. All right. These are possible. Yes.
The presentation says a number of the from a plus b I. Form or from?
Form.
Okay.
A plus bi. Any number in this form is a complex number. Complex. All right, so I'm going to write down some possible numbers for this. All right, here is an example. 3 plus 2i. 3 plus 2i. All right, that is a complex number. Now, the complex number have 2 parts. The complex number has the real part, and it has the imaginary part. All right? So it is our job to be able to understand, to recognize those values. Let me ask you something. Please, guys, in the chat, tell me what is the value of the real part in my example. All right, people are answering now. Beautiful, beautiful, beautiful. You guys are correct. The real part is 3. Absolutely easy. And now guess what? Guess what I am going to ask you. What is the imaginary part? The b. All right, beautiful stuff. 2. Now, some people might say, teacher, the imaginary part has to be 2i. Not really. Again, according to our definition, the one that is in the presentation here, this part, the second part, where is it? There, the second part, b is called the imaginary part. Just b. B alone, not bi. No, just b. In this case, b is just the letter 2, the number 2. So we have the real part 3 and the imaginary part 2. That's it. That is it. Now, let's jump into a harder one. How about this number? Is this number complex or not? All right, let's see. 4i minus 6. Is that a complex number or not? All right. So before we jump into knowing if it is or not, we need to know how do we know if it is or not. Simple. If it is in this form, so a real part and an imaginary part, if it has that configuration, it is a complex number. If it doesn't have that configuration, it is not a complex number. So is it a complex number or not? In the chat, please. Some people are already answering. Okay. All right, cool. All right, cool. You guys are correct. It is a complex number. It is a complex number. It is our job now to find the values of A and B, the real part and the complex part. So let's begin with the easiest. What is the real part? Okay, we have 2 answers correct. Oh, beautiful, beautiful. Man, you guys did not forget about the negative. Beautiful. The negative 6 is the value of A. Negative 6. Remember, signs belong to the number. So in here I have a negative 6. That is part. I have a negative. That is part of the 6. So negative 6. And let's jump into the second part. What is the imaginary part? B. The easy, right? The easy part. 4. Beautiful stuff. Beautiful stuff. But we can continue. We can do this even further. How about this? How about this? This is my example. Pay attention to it. 9i. Is this a complex number? Yes or no in the chat, please. Let's see what you guys say. Let's see what you guys say. All right, let's see what you guys say. Okay, all right. Okay, we have a lot of answerings. We have a lot of answers. All right, cool. All right, let's see. So before, again, remember, to know if 9i is or not a real number, I'm sorry, a complex number, we need to have this configuration, a real part and an imaginary part. Now, for what I can see, we can clearly see the value of B, the imaginary part. That is 9, right? B, the imaginary part is 9. But there is a problem with my number. I don't have an A. I don't have the real part. I don't have plus something. What do I do? Or do we have it?
We have 1. The real is 0.
Yes, sir. Just like Danny said, and a lot of other people in the chat said, we do have a real part. The real part is 0. A, the real, is 0. So we have 9a plus 0, or 0 plus 9i. We have real part and complex part. So every single number like this is also a complex number. But we can take it even further beyond. Look at this. Look at this. And I assure you, this is going to blow your mind. This is going to blow your minds. Look at this. How about this number? Is this a complex number? Yes or no? In the chat, please. Okay. We have some people answering. So far, I only see one right answer. Because for us to know if this is a complex number or not, it has to have this configuration, right? It has to have this configuration. And I don't see the I. I mean, I clearly have a real part, right? A equals 27, right? I clearly have the real part. But what about the B? There's not a B. Or is it? Just like in this example, the value that did not appear was 0. In here we have plus 0i. 0 times anything is 0, so we can just forget about this. 27 is the same as 27 plus 0i. So we have the value of B. We have our complex number. We have our complex number. But this one is one of the real numbers that you guys usually use. So what I'm saying is, okay, you might be thinking, teacher, so what you're saying is all this time, we have been using complex numbers? Yes. Yes, we have. We have been using complex numbers. We just never told you about them. We just never introduced you the name. But we were using these numbers. 27 is a regular number, but that one is an example of a complex number. So every single number that you all know, every single one of those is also a complex number. Because all you have to do is add a plus 0i. And you're done. You have your complex number. Eh? Man, I know this for the longest time. But even I, get my mind blown by this. Man, this is so beautiful. All right, let's continue with the presentation. So we know this part, right? We know what is a complex number and how to identify if a number is a complex or not, right? But how do we know if two numbers are the same? Look, what I'm showing you right now in this slide are to the left of the equality. Locate the equality, please. Locate the equality. In the middle, there's an equality, right? To the left of the equality, we have the number a plus bi. Those are not two numbers. No. That is just one number, one complex number. Right? Remember, whenever you find a plus bi, that is just one number, a complex number. And to the right of the equality, we have also just one number, a real part plus a complex part. In this case, c plus di. All right? So we have two numbers being equal. How do we know if those two numbers are equal or not? Simple. We're going to look at the real parts. If the real parts are the same, so a and c are equal, a and c, the real parts of each complex numbers, if those two are the same, but also the complex parts are the same, then we say the numbers are equal. All right. Now, equality of complex numbers, you guys are gonna use it probably if we talk about equations with complex numbers, but I don't think we're gonna have the time. All right. So we can just skip that part. But we cannot skip this. All right. Let me change into the previous form. There we go. Addition and subtraction of complex numbers. since we have numbers, we can add them and we can subtract them and we can multiply them and divide them and do a lot of things with them. And we will in this group, in this class. We will do a lot of that in this class. Look at this. How did you guys add two complex numbers? Let's say we have 2 plus 3i. And we are going to say plus another one, 5 plus 6i. How are you guys going to add those two? We have a simple addition of numbers, 1 plus another one. How? If these were real numbers, the usual numbers, we would go something like this, 2 plus 5. And that we know, that is 7. We know that. That is easy. But how do we add the complex numbers? Look at what I say in the presentation. Just add the complex numbers. Oh, let me do the example first, the example later. Just add the like terms. Look, A with C, those are the real parts, and then B with D, B with D. Huh? Somebody said it in the chat. Ethan said it in the chat. Perfect stuff, Ethan. In my example, locate and add with like terms. So 2 plus 5 and 3 plus 6. That's it. Another way of looking at it is adding these numbers as if you guys were in third grade. Look at that. We are going back so far. When you were in third grade, you didn't add the numbers like that. You add them like this. 2 plus 3i, and then 5 plus 6i, and then a plus, and like that. When the numbers were big, right? When the numbers were big, you needed to add like this. Well, if we add like this, 2 plus 5 is 7, and 3 plus 6 is 9. So we have our solution. 7 plus 9 I, the solution. 7 plus 9i. Man, so beautiful and so easy. And so easy. All right, let's look at the example. Let's look at the examples. We have one example here. 3 plus 2i plus negative 7 plus 4i. Remember, like terms. Real with real, imaginary with imaginary. So 3 plus negative 7 is negative 4. And 2 plus 4 is 6. So there we go. We have our answer. But how do we subtract? How do we subtract? Exactly the same. But instead of adding the like terms, we're going to subtract the like terms. The same example. 3 minus negative 7. 3 minus negative 7. Again, real part with real part. So 3 with negative 7. Those are the real parts, right? 3 minus negative 7. Then we're going to have this as a positive. So 3 plus 7. That is 10. And also 2 minus 4. That is negative 2. Don't forget about the I, and we are done. Now, we can do the same with my example in the board. Look at my example. What if we wanted to do a subtraction? 2 plus 3i minus 5 plus 6i. Go ahead and write it in the chat if you know the answer. Let's see who is faster, you or me. So we're going to write it like this. 2 plus 3i minus 5 plus 6i. Now, 2 minus 5. Now, the operation is minus, so I'm going to do the minus like that. 2 minus 5, that is negative 3. And then 3 minus 6. 3 minus 6 is negative 3 as well. So we have negative 3 minus 3i. You guys, you are faster than me. All right, pretty good. Pretty good. Shh. Pretty good, guys. Pretty good. Congratulations. All right. Okay, pretty good. Now, those were additions and subtractions. Can we do more? Can we do multiplication? Yes, we can. But I don't think we're going to do it today. I don't think we're going to do it. Oh, man. Yes, we are. We are going to do it today. We are going to do it today. All right. Product of complex numbers. And this is where things begin to be a little bit more interesting because additions and subtractions were pretty simple. Simple things are not that interesting. Multiplication, on the other hand, if you want to multiply, you need to know how to add and subtract. So these have two levels. This is some interesting stuff. Here's an example. Always, whenever you want to multiply the numbers, you need to use FOIL. All right? Now, did you guys study with someone who explained what FOIL is? All right, beautiful. All right, cool. So guys, please, in the chat, someone explain to me what is FOIL.
FOIL means first, outer, inner, last. That's the order that you use to multiply.
Yes, sir. First, outer, inner, and last. Yes, sir. And that is exactly what we are going to do here. We are going to do the firsts, which are 3 times negative 7, negative 21. Firsts, 3 times negative 7, negative 21. Let's continue with first, so outers, right? 3 times positive 4i. 3 times 4. So 3 times 4 is 12, and don't forget about the I. This multiplication is done just like you would do with regular numbers. If this was an x, you have 3 times 4x. That is 12x. Exactly the same. So we have 3 times 4i, we will be 12i. We are an outer. So now let's go with inners. 2i plus negative 7. So positive and negative, that will be negative. 2 times 7, 14, and the I. Negative 14i. Beautiful stuff. But now the L, the last. 2i times 4i. All right, 2 times 4 is 8. I times I squared. right? I squared. But are we going to leave that answer there? No. We can do two things. Number one, we can do like terms just like Richie said. Pretty good, Richie. But also, we have the definition. The definition of imaginary unit. I square. This I square is a negative one, right? Wait, somebody's jumping a little bit more. Let's switch into this presentation. Let me explain it here. We have a negative, we have a I to the 2. I to the 2 is negative 1, right? So if I copy just everything, we have 3 plus 2i times negative 7 plus 4i, right? Doing the multiplication, doing FOIL, we have negative 21 plus 12i minus 14i plus 8i to the second power, right? We have that. This looks bad in camera. There we go. Looks better. And this is an I. All right. But before we do like terms, we know that this I to the second power, that one, this is negative 1. So if we rewrite everything, we will have negative 21 plus 12i minus 14i minus 8. Why minus? Why the positive became a negative? Why the positive? Focus camera, please. Okay. There we go. Why did the positive became a negative? What happened? Why did the positive became a negative? Because we have 8 times negative 1. So we have positive times negative and 8 times 1. Negative 8. Eh? Why did I change the I square as a negative 1? Because that is the definition of the I, of the imaginary symbol. So now we can do like terms. We can do these two, negative 21 and negative 8. Those are like terms. And we have 12i and negative 14i. Those are other like terms. The final solution. Negative 21 minus 8 will be negative 29, right? And then positive 12i minus 14i. This will be negative 2i. Our final solution. Let's see if you guys got it in the chat or not. I don't know why the chat's not charging. There we go. Yes, somebody got it. Parrado. My man. Yes. My man. All right. Let's continue then. And the final solution. There we go. Final solution. Now, the conjugate. I'm going to stop here and we're going to see this the next class, all right? The next class. Because I don't want us to know a lot of stuff and don't practice. I don't want that, all right? I don't want that. So if you want to study this at your own pace, you can go ahead and do so. Look, here's a definition of a conjugate and then some examples and all of that, right? And we have some exercises. But we're not going to do that now. We're not going to do that now. We're going to stop here at product of complex numbers. What I want you to do, guys, is to please go to Alex. Go to Alex and work on the classwork there. Yes?
So it is a complex number because have the like the form.
Mm-hmm. Yes, sir. Yes, sir. This one, it has the form of a complex number, right? We have a real part and we have an imaginary part. The real part is going to be negative 29 and the imaginary part is going to be negative 2. So this one is a complex number. Complex number. Let's write it like that. A complex number. It is a complex number, right? It is a complex number. But look at this. This was a complex number too, and this was a complex number too. So whenever we multiplied complex numbers, the solution will also be a complex number. And whenever we add complex numbers, the solution was a complex number. Same with subtraction. Will that happen with division? If I take two numbers and I divide them, will the solution be a complex number? Hopefully, yes, but we don't know because we haven't seen division. We will see that later. But Parrado, you are correct. This solution was a complex number because it has the form. Yes, sir. All right, I'm gonna stop the video now. I'm gonna stop the recording now. And if you have any questions about the classwork, right? You can always ask me, right? Remember, if you have questions, I will begin the recording again. All right, guys, let's see. There we go.